Welcome to This Explainer. You know, whenever we think about space exploration, our minds usually jump straight to the thunderous roar of rockets and the incredible physics required just to break free of Earth's gravity. But honestly, getting to space is really only the first part of the battle. Today, we're going to explore the incredibly hostile physical conditions a spacecraft absolutely must survive once it actually gets up there. The space environment is entirely unforgiving, and designing machines to operate out in the void pushes our engineering capabilities to their absolute limits.
Just think about this for a second. How can one single invisible particle take down a billion-dollar satellite? I mean, it sounds like the plot of a science fiction movie, right? But this isn't fiction. Out in the vast, empty void of space, the most catastrophic threats to our advanced technology aren't necessarily giant asteroids or debris. Often, they're entirely invisible to the human eye.
Okay, let's dive into this with Section 1, the invisible bit-flipping threat.
To really understand this threat, we have to look way, way down at the microscale. Spacecraft are continually bombarded by high-energy radiation, and this creates a totally bizarre phenomenon known as a single event upset, or SEU. An SEU is basically a change of state caused by just one single ionizing particle striking a highly sensitive node in a microelectronic device. Imagine a microscopic cannonball slamming directly into the delicate, intricate circuitry of a computer chip. So, why exactly does radiation flip these satellite bits? Well, we have to remember how computers actually think. They store data in binary code, just zeros and ones, and these are physically represented by tiny, microscopic electrical voltages inside memory chips. When a highly energetic ionizing particle from space radiation strikes one of these sensitive nodes, it deposits a microscopic trail of electrical charge, and if that sudden burst of charge is strong enough, it can literally shift the voltage. It changes a 0 into a 1, or a 1 into a 0. It literally flips the bit. It's essentially a cosmic typo, and if that single tiny bit happens to control, say, a critical navigation thruster or a life support valve, well, that single particle could cause totally unexpected and disastrous behavior. That's exactly why engineers have to build in complex error detection and correction systems to constantly check the math and fix these radiation-induced typos on the fly. Now, what's really interesting about this is that this radiation isn't just coming from one place. Spacecraft are caught in a massive cosmic crossfire. They're bombarded by continuous solar radiation from our sun, plus those unpredictable, violent solar particle events. Then you've got galactic cosmic rays, which are these incredibly high-energy particles blasting in from deep space way outside our solar system. And even if you're orbiting close to home, you still have to navigate Earth's own radiation belts, these intense zones where our planet's magnetic field actually traps charged particles. It's a remarkably complex hazard zone.
All right, zooming out to our next section, the broader hostile environment. Stepping back from that microscopic scale, we face the massive macro hazards of space. And when you compare Earth to space, the stark reality becomes pretty obvious. Here on Earth, we are incredibly spoiled. We're completely protected by a thick, comforting atmosphere and a powerful magnetic field that shields us from the worst of the universe's hostility. But space? Space is just a hostile void. It's defined by extreme physical conditions that actively degrade, fatigue, and damage materials, electronics, and mechanical systems. When a spacecraft leaves Earth, it literally leaves all of its armor behind. Section 2. Surviving the breathless vacuum. That brings us to our second major environmental hazard, and it's probably the one we most commonly associate with space: the breathless, empty vacuum. Space is almost a perfect vacuum. There is virtually no air and no atmospheric pressure. Now, on one hand, this sounds absolutely amazing for travel, right? Because there's no air resistance or drag. Once you get moving, you just keep moving without needing to constantly burn fuel. But from an engineering standpoint, the lack of air creates an absolute nightmare for the materials the spacecraft is actually built from. These vacuum engineering challenges are frankly fascinating. Because there's zero pressure, materials behave completely differently than they do on Earth. Take outgassing, for example. Common materials like adhesives, plastics, and lubricants contain volatile compounds. In a vacuum, these compounds literally boil off and turn into gas. This outgassing creates a weird sort of cloud around the satellite, and those gases can actually condense onto delicate optical instruments, permanently contaminating million-dollar camera lenses or totally degrading solar panels. Also, think about heat.
On Earth, if your computer gets hot, a fan blows air across it to cool it down through convection. In space, there's no air to blow. Heat transfer can only happen through radiation, which makes thermal management incredibly difficult. Moving right along to Section 3, Atomic Oxygen's Hidden Danger. Speaking of the atmosphere, or the lack thereof, there's a highly specific, totally hidden chemical threat that lurks right on the edge of space, specifically in low Earth orbit. It's called atomic oxygen. Now, the oxygen we breathe down here on Earth comes in pairs, 2 oxygen atoms bonded together, O2. But high up in low Earth orbit, intense ultraviolet radiation from the sun blasts these O2 molecules apart, creating single, highly reactive oxygen atoms. And because satellites in low Earth orbit are zooming around at roughly 17,000 miles per hour, they are constantly, aggressively plowing right through this invisible field of single oxygen atoms. Because these single atoms are so chemically unstable and highly reactive, they literally eat away at the spacecraft. It's wild. Over years of operation, atomic oxygen will severely erode exposed materials. It chemically reacts with and strips away thermal blankets, degrades structural polymers, and attacks the solar panels. To survive this invisible acid bath, engineers have to develop and carefully apply highly specialized protective coatings to the very outer skin of their satellites. Section 4. The Extreme Thermal Roller Coaster. And this brilliantly illustrates our next massive hurdle. As if radiation, vacuums, and corrosive atomic oxygen weren't enough, spacecraft are subjected to violently rapid temperature extremes. When a satellite orbits Earth and moves into direct, unfiltered sunlight, the temperatures on its surface can soar above a blistering positive 120 degrees Celsius. That is hotter than boiling water. The spacecraft is literally baking under intense solar radiation without any atmosphere there to diffuse the heat. But then, literally just minutes later, the satellite crosses behind the Earth and plunges into the eclipse shadow. Without the sun's rays, the spacecraft is instantly thrown into a freezing, pitch-black darkness, where temperatures plummet well below negative 100 degrees Celsius. This relentless back-and-forth swing is called thermal cycling. Now, as you know, heat makes things expand, and cold makes things contract. Going from boiling to freezing over and over again causes intense thermal expansion and contraction. Imagine taking a paperclip and bending it back and forth. Eventually, it just snaps, right? That is material fatigue. The structural joints, the sensitive batteries, the electronics, they all endure heavy physical stress. Engineers absolutely have to overcome this by using a smart mix of passive control, like specialized reflective paints, and active control systems, like fluid loops. In fact, the International Space Station uses miles of piping filled with liquid ammonia just to pump heat away from its living quarters so the astronauts don't overheat. It takes massive, constant effort to keep internal components at a stable, survivable temperature. Finally, Section 5, Designing for Mission Success. Let's move to this breakdown and see how this all builds into a cohesive strategy. Here is our engineering battle plan against the void. To stop radiation from flipping our computer bits, we use sophisticated air detection and heavy radiation-hardened components. To stop vacuum outgassing from ruining our cameras, we meticulously select only vacuum-compatible materials and pre-bake them before they ever launch. To fight atomic oxygen in low Earth orbit, we armor the spacecraft in specialized resistant coatings. And to survive that brutal boiling and freezing thermal cycling, we meticulously map out both active and passive thermal control systems. So the crucial point to take away from all this is that understanding the space environment isn't just some academic exercise. It is the fundamental driver of space systems engineering. Every single factor we've discussed today, the vacuum, the radiation bit flipping, the extreme thermal cycling, it directly dictates material selection, structural design, electronic choices, and thorough risk assessment. Accounting for these invisible forces from day one of the design phase is literally the only way to ensure the ultimate lifespan, reliability, and mission success of any spacecraft. Which leaves us with this final thought. We've spent decades mastering the hazards of Earth orbit. We know how to shield our bits from radiation and insulate against the freezing shadow. But as humanity sets its sights on returning to the moon, pushing out to Mars, and venturing even further into the uncharted depths of our solar system, well, the environments are only going to get harsher. The radiation will become more intense, the temperature extremes more punishing. So as we push further into deep space, what unknown extreme will our technology have to survive next? Thank you so much for exploring the hostile void with me today in this explainer. Keep looking up and keep questioning what it takes to survive the final frontier.